the question answer.
Is my screen visible?
Yeah, please go ahead.
Okay, hi everyone. My name is Saksham Bansal and I'm from NSUT Delhi. I'll be presenting my paper, a multitask multimodal framework for tweet classification based on CNN, which was um, for the Me Too Grand Challenge submission organized as a part of the uh, Big Data on Multimedia IEEE conference. So the agenda for the presentation is as follows. I'll begin with a quick introduction about the Grand Challenge, followed by describing the dataset. Then I'll describe our pre-processing techniques and my proposed solution for the Grand Challenge submission. Next, I'll dive into some of the experimental setup details, finally describing the results evaluation and discussing future work and improvements upon our submission. So the Grand Challenge is basically focused on the multimodal aspects of the Me Too social movement. So as we would all know by now that the Me Too movement is one of the most powerful movements against sexual assault and women's rights in recent history. And the movement saw it spread through Twitter, where users would post their stories with the Me Too hashtag. So this creates an opportunity for researchers to understand how people are expressing themselves in informal settings and understand more about colloquial language. So the challenge basically involves building a multimodal framework for predicting the various linguistic aspects of tweets such as relevance stance, hate speech, sarcasm, and dialogue acts. And for the challenge, we try several different approaches, and I'll be describing our approaches based on bidirectional LSTM and convolutional neural networks. So the data set that we were provided as a part of the challenge consisted of 9,973 tweets that were manually annotated by human experts across the 5 different linguistic aspects. And on the table, you can see the 10 different labels that we have where the tweets were manually annotated. And as should be evident from the table, there's a significant class imbalance for most of the labels in the dataset, most notably for um, refutation, sarcasm, and generalized hate, where we have more than 90% of the labels are marked as negative. And so I'll discuss our uh, techniques for dealing with class imbalance later on in the presentation. Okay, so now moving on to the pre-processing. Uh, Before using the dataset directly for training our models, we use several pre-processing techniques, and the reason for this is because we observe that the tweet text often contains numerous items such as URLs, emojis, hashtags, and special characters that increase vocabulary size significantly and add noise. So I'll describe the pre-processing techniques we use with a few examples. So if you see the first row of the first example on this table, it shows don't count your emoji before the emoji, where the author implies don't count your chickens before the hatch. Now, simply removing the emojis would cause the sentence to lose its meaning. So we use a Python library called emojis to convert the emojis to text. And so we have, after pre-processing, we have don't count your front-facing baby chick before the hatching chick, which is not exactly the same as don't count your chickens before the hatch, but it still keeps the meaning intact. And secondly, we definitely remove all the URLs because they do not add any meanings to the sentence and perform word segmentation. So I'm with her is changed to segmented and is changed to I'm with her. And lastly, we also do normalization to reduce the vocabulary size. So for example, we have 365 days here. And so in the preprocessed text, we have number days and number millions. So all the specific numbers inside the text are replaced by the number class, and we do this similarly for all the dates, time, currencies, etc. And as you can see, the fist emoji is replaced by raised fist here. So now moving on to our proposed models for the challenge. We first try to build the multitask models on individual modalities, that is text modalities. So I'll be first describing our models um, we use for text classification, which is bidirectional LSTM and convolution neural network. And then I'll be moving on to our model for image modality, which is CNN. And then lastly, I'll be describing how we combine the results from these two modalities using multimodal fusion techniques. So as we know that biosystems have been shown to be effective for sequence classification tasks as they can capture long-term dependencies. So we use a biosystem which has the advantage to consider the entire input sequence at each time step. And so we use the output from the biosystem to pass to multiple multi-layer perceptrons the for classification part for the 10 different labels. So so we use 10 different multi-layer perceptrons for um, classifying the 10 different labels. So here we're using hard parameter scaling.
So sorry to interrupt. You have last 1 minute.
Okay. And so the next model we have is CNN for text modality, where we um, use the filters from CNN to represent construct features from the text and pass them to different multi-layer perceptrons. And then finally, for image modality, we use a ResNet model for fine-tune a ResNet model that has been trained on the ImageNet dataset. But from the image modality, we do not get significantly better results. So we do not use the model for in the final multimodal model. We only use it for the image only informative label. And for the rest of the labels, we only use the text modality results. So this basic experimental setup, we use 200-dimensional glove embeddings. And to deal with the class imbalance problem, we use cost sensitive learning, where we use different weights with the cost functions to offset the class imbalance. So for example, the positive class has a higher weight so that it has a more effect on the final output of the model. And finally, we train the models for 3-4 epochs with early stopping. So the final results from the models are shown on this table. We observe that the CNN model outperforms the BiLSTM model. And so we use that for a final submission combined with the ResNet model. And so the future work for the challenge could be we could have tried using transformers such as BERT, which have achieved state-of-the-art results.
Okay, thanks Aksham. I believe we got it. Thank you so much. So any questions from the audience?
Have a specific reason on selecting glove 200 dimension embeddings?
Yeah, the glove embeddings had been were trained on the Twitter dataset. So I think that was one of the reasons. And also I tried using fast text embeddings, but they did not show any significant improvement in the model. So I just stuck to glove.
When you say significant, how did you compare that exactly? Like, what was your comparison in terms of choosing how to encode tweets?
Um, so the AOC scores from cross validation, I used cross validation for on the validation set. So the scores that I got from the models by using fast text embeddings were not significantly better than using the glove embeddings.
When you say significantly, do you mean under a statistical significance test, or do you mean just based on the absolute numbers?
Yeah, I think just based on the numbers.
All right. So let's say you did one run with glove on the val set, and then you did one run with fast text on the val set. You compared these absolute values, and you thought that these don't look significantly different. So then glove is probably the way to go.
Yeah, we did. Actually, I did cross validation, and we did average of 5 runs. So I compared the average of 5 runs for with the fast text and the glove embeddings. Yeah.
Okay, got it. Second question on the multimodal aspect. How did you, either we missed it because of the time aspect, but could you elaborate just a little bit on how you're combining the image modality with the text modality?
Yeah, sure. So I was using late fusion where I basically took the predicted probabilities from the image model and the text model and concatenated them and passed them to the multilayer perceptron for making the final output.
Did you try something like early fusion to contrast with, or was late fusion the only thing you tried?
Yeah, I only use late fusion, but in the future work, I did mention experimenting with different fusion techniques could have been.
Yeah, just a question.
Okay.
So, how are you obtaining the prediction probabilities for the images?
So, so we were fine tuning the ResNet model. So the
Okay, okay, fine. Sure. Thanks for the clarification.
Okay, then thanks. I believe this much time we have for this presentation. Thank you so much, Saksham. So the next presentation will be from Priyam Bashu. So Aryan, please help him.
Yeah. Can I get screen share access?
Yeah. So Aryan, could you please provide?
Yeah.
Just a second, sir. Just a second.
Sure.
Also, we've provided in the presenters.
Yes, I've got. Can
So
you see
Priyam,
this?
you have 12 minutes.
Yeah. Is my screen visible?
Yeah, please go ahead.
Okay. Good evening, everyone. My name is Priyam Basu. I'm currently an undergraduate student at Manipal Institute of Technology, Manipal campus, and I'm under the EEE department. And today I'll be presenting our paper, Multimodal Sentiment Analysis of Hashtag #MeToo tweets using focal loss. So let's start with the introduction. So various studies over the world have indicated that approximately 1 in 3 women has experienced partner or non-partner violence, be it physical or sexual. So the movement in itself has led to people talking about personal experiences of harassment more openly. The hashtag #MeToo movement, with variations of related local or international names, in its essence is a movement that against social harassment and sexual abuse, which has seen a lot of participation from all over the world, usually falling victims to powerful and influential people. It has also been found out that in most cases, the woman was harassed by someone she knows, and hence people should be educated from a young age so that they can speak against such predatory behavior if they ever fall victim to it. Hence, it is very important for us to understand the public stance on such very on such very sensitive topics in order to educate the masses and create more public awareness. Objective and data. So the objective of this paper is to analyze the public sentiment of the hashtag #MeToo movement using information based on tweets with the hashtag #MeToo in it collected over the months of October, November, and December. We try to understand relevant problems affecting the current social media space. We propose an approach of multimodal sentiment analysis by combining advanced transformer architectures for text analysis as well as deep neural networks for facial analysis. The tweets in the dataset have been manually notated into 5 linguistic aspects as mentioned: relevance, stance, hate speech, sarcasm, and dialogue act, which have been further divided into features having binary values of 0 or 1. The goal of this paper is very different from the standard sentiment analysis goal of predicting whether a particular piece of text has positive or negative connotation, but rather understand the public stance on the topic based on a variety of sentiments and emotions. So we tried out various machine learning and neural network architectures, but finally decided to stick with ResNet 152 for image analysis and both for text analysis. So the tweets in the dataset were the original tweet IDs. We had about 9,973 tweet IDs, out of which we were able to scrape only 6,809 tweets. And the tweets had text as well as an image attached to them, most of which were memes. The text contained alphanumeric characters, special characters, and emojis. And as mentioned earlier, it was collected over a period of 3 months. So we performed some data analysis, an exploratory data analysis on the data that we were able to scrape, and these are some of the insights that we got from the data. So as you can see in table 1 over here, this shows the data imbalance. So one of the major challenges that we faced while working on this project was the high class imbalance. So as you can see, so it is a multi-label binary classification problem where we have 10 labels and 2 labels of 0 and 1. So you can see the ratio of zeros and ones over here. So for textual informative, it was 0.27 to 0.72. Image only, it was 0.66 to 0.33. Reacted heat was 0.96 to 0.03, and so on. So as you can see, that there's a high imbalance in the data over here. So initially, when we were evaluating our models on just based on an simple accuracy metric, all of them were giving very high accuracies of 96, 97%. But on finding out further imbalance in it, on realizing the imbalance in the table, we realized that the model was mostly overfitting. That was one of the issues that we faced earlier. Then we tried to analyze the data some more, and then so in table 2, as you can see, so table 2 shows the frequency column, shows you the number of tweets which belong to class 1 for feature 1 as well as feature 2. So as you can see, out of the 6,809 tweets, 143 of them had allegation belonging to class 1 and directly belonging to class 1. And you can see there were 280 tweets where support and allegation both belong to class 1. This shows us the interrelation between the different kinds of sentiments that we have. And the table that you can see at the bottom is basically the data that we scraped. So this is the text and the corresponding classes belonging to each of the labels. And each of the text also had an image attached to them. So on further analysis, we generated these word clouds. So these are 4 of the word clouds that we generated for justification, directed hate, allegation, and generalized hate. So over here, you can see, for example, if you look at the justification word cloud, and you can see Anu Malik over here. So Anu Malik was accused of sexual harassment by various Bollywood personalities. So that's why, but then he had gotten a large amount of support from his followers who had tried to justify his actions, who were trying to justify him. So that is some kind of insight that we got. As you can see in the directed hate column and in the allegation column, you might see the term BCCI over here. You can see it over here as well as over here. So this is something that also tells you that so the BCCI CEO Rahul Johri was in 2018 he was accused of sexual harassment, and therefore there was a large amount of hate and there were a large amount of allegations against him, and people were coming out regarding him on Twitter, and that's why you can see his name and you can see that in the word clouds over here. So this basically shows us the most frequent words that are being used by people for each of the labels when they're trying to portray a particular kind of sentiment. Next is, as mentioned before, we made the use of ResNet. So ResNet is an artificial neural network which uses skip connections to jump over some layers to avoid the problem of vanishing gradients by reusing the activation functions, or by reusing the activation, of the previous layer until the adjacent layer learns its weights. We've made use of ResNet 152, which is a ResNet architecture that has been trained on the ImageNet dataset. It has been used as an image encoder network over here. The general architecture has been kept the same. We removed the last 2 layers from it. The second last layer was an adaptive average pooling layer, and the last layer was the classification layer. So we removed those 2 layers to obtain the image embeddings from there. And the image embeddings that were obtained from there were initially of a shape 2048 dimensions, and we reshaped that to get them into layers of 768 dimensions each. Then for the text analysis part, we made use of BERT. So BERT stands for bidirectional encoder representations from transformers. It is a Boolean transformer architecture used for a variety of NLP tasks. It has 12 layers, 768 hidden layers, 12 heads, and is trained on 110 billion parameters. So text was then passed through a code tokenizer, and after we obtained the tokens from that, then whatever tokens we got from this, so the CLS tokens, the separator tokens, the text embeddings, and the image embeddings, they were then concatenated together. And after being concatenated together, we got the image embeddings as well as the text embeddings, and that was a resultant vector of 768 dimensions, and that was then passed on to a batch normalization layer. As you can see here, we have tried to show the model architecture. So here you can see is the original image. So the original image is then we perform various image transformations on that, and so we normalize the images, and the final image that we get is of dimensions 224 by 224 by 3. It is then passed through a ResNet 152 image encoder. We get the image embeddings from here. We've taken 7 image encodings and they were of 2040 dimensions each. Now we have passed them through BERT embeddings, and we have reshaped them so that we get 7 image embeddings of 768 dimensions each. Now we have done this because the output vector for BERT embeddings are of 768 dimensions. So in order for us to concatenate the image as well as the text embeddings, they need to be the same shape. That's why we have reshaped them over here to get 768 dimensions. Then you have the input text over here. The input text you had gotten from the tweet. So the text is then passed to a BERT text tokenizer. You get the tokenized text. You pass them to BERT embeddings, and then you get the text embeddings over here. So now you have the image embeddings and the text embeddings from these two layers, and then you concatenate them. After concatenating them, you get the concatenated image and text embeddings. They are then passed into a BERT encoder. After that, the outputs are pooled. The pooled outputs of the last hidden state of BERT encoder is then passed through a batch normalization layer, which is then eventually passed on the classification layer, which gives us the output. Experimental setup. So as mentioned before, a major problem that we faced while working on this project is a high data imbalance. So we tried to fix that by duplicating the underbalanced class. So like the number of, in most of the cases, the number of ones we had belonging to a particular label was quite less. So we tried to duplicate that. So we tried out, we had 4 models in total. The first model worked on without duplication. The second one had the data duplicated only once. The third model had data duplicated twice, and the third model had data duplicated thrice. So we had 4 models in total that we had tried out. Then the optimizer we used over here was Adam optimizer. We used reduce LR on plateau learning rate scheduler. So what this does is that whenever the learning rate reaches a point, whenever the metric reaches a point that the model does not improve anymore, it reduces the learning rate. And we have seen, it has been statistically seen that models often improve from reducing the learning rate by a factor of 2 to 10 once the learning rate starts to stagnate. Apart from this, we have also another technique that we used to tackle the data imbalance problem was using the focal loss. So focal loss is a kind of a loss function that assigns a greater penalty for wrongful predictions of underbalanced class. So what happens is that the weights of the loss due to the correct classification are reduced, whereas the weights for the loss due to misclassification remain the same, and that way it gave us better results. We also implemented.
So Priyam, sorry to interrupt. Last 2 minutes.
Yes. Apart from focal loss, we also implemented dice loss, but then we saw that focal loss gave us better performance. And yes, and as mentioned before, the number of image embeddings we took was 7. So these are the results that we obtained. So table 3 and table 4 will show you the AUC scores for each of the labels that we had, and it shows you for each model. So no duplicate means the data wasn't duplicated. Single duplication means for the data underbalanced class was duplicated only once, and here twice and thrice. So, and here you can see that the triple duplicate model does not always have the optimum results. or the no duplicate model does not always have optimum results. So like this was performing differently for different labels. Different models perform differently for different levels, and they weren't really following any pattern as such. And apart from that, we have the ablation results over here. And future prospects. So yeah, we would like to further improve upon this project. Right. So the whole objective of this project was to understand the public sentiment on the hashtag #MeToo movement. So up until now, it was based on the data of only in the months of October to December of last year, only Twitter. So we would like to scrape more data from more social media websites and try to get a better understanding. And apart from that, so our model made use of two main architectures. One was BERT and one was ResNet. So instead of BERT, you would try to use the newer transformer architectures such as Robota, which is a robust BERT basically, and Big BERT. Apart from that, instead of ResNet, we would try to improve upon the ResNet architecture as well. We would try to use Inception ResNet or VG networks, etc., and look for different visual recognition models. And yes, so up until now, we were using focal loss. We also implemented dice loss, but we saw the focal loss was giving us better results. We tried to further delve into what different focal losses could help us improve upon our model based on the current data set because of the high data imbalance.
Thanks.
Yes,
So questions? Yeah, questions?
Did you fine tune BERT?
Did we fine tune BERT? No. Use the baseline.
Why did you use this? Why did you use the CLS token then?
We used a BERT-based uncaged model. We were actually implementing, so the MMBT paper that was released by Facebook last year, we had implemented the same paper, and we had to implement that paper, and we instead of using the standard loss function, we used focal loss to improve upon the data imbalance.
Yeah, I get the data imbalance, but I'm talking just about the text embedding, nothing after that. So you mentioned that you're using the CLS token.
Yeah.
Usually what I understand based on BERT is that you use the CLS token if you fine-tuned it, because the CLS technically is, let's say you did some fine-tuning for the classification task, that's when the CLS token would be a more comprehensive sentence representation to encode the tweet. So just wondering why was your choice the CLS token if you've not fine-tuned BERT?
We actually, we were just using our baseline model all throughout. So we were trying to implement FAIR's MMBT model, and in that model they had used CLS tokens. So we just tried to use that. That is the reason why we used.
Had they fine-tuned BERT, or do you not know that?
Yes, I think they had. Yes, they had improved models. They had multiple models that tried to improve upon their MMBT structure.
Okay, makes sense. Usually what I've seen in practice is if you don't specifically fine-tune for BERT, it also makes sense to just take the output token from all the layers and just do an average of that. Usually ends up working better than CLS if you're not fine-tuning, but okay, makes sense. Okay. Second,
we were trying to use it actually for to act as a separator while concatenating the text and image embeddings.
Okay.
Yeah.
Second, you mentioned an interesting aspect that when you add the number of duplications, like when you do double, triple, etc., you can't really see consistent improvements across multiple tasks. In fact, based on what I saw in the tables, it seemed like the triple and double are mostly reducing performance, especially in the image informative case. Why do you think that's the case? Like, I understand that comes out empirically. Why do you think it leads to a performance reduction?
It does not always return to a performance reduction. So like when initially the models that we had trained, they were on no duplication. So after that, we just tried to, by that time we had already implemented focal loss. We were trying to think of newer methods to improve upon try to tackle the data imbalance problem. So somewhere we saw how to the data duplication. So we did it just for one label, and then our overall score improved. And then we did it twice, and then for some other label it improved. So what we saw that for different labels it was working differently. Like there was no particular pattern it followed. For some it increased, for some with duplication it increased, but for some with duplication it decreased. For some with by increasing number of epochs it was increasing, for some it was decreasing.
Got it. But you've not done any kind of qualitative analysis to try and see why that's happening, or for what kind of examples that's happening? Like what you're telling me seems to be more of an empirical observation. I'm just trying to wonder
Yeah.
if there is like a reasoning behind why it's happening, or if that's just like empirically and you've not seen why that's happening by looking at the actual images and such.
I was actually empirically concluded. We did not do any further analysis into that.
Okay.
Are there any other questions?
Now it seems there are no more questions, so I think we can proceed ahead with the next presentation.
Yeah, it seems no more questions. Thanks, Priyam. So
Thank you, sir.
let's move to the next presenter. Vedant, will you be presenting?
Actually, Aman Priyanshu will be presenting.
Okay, sure. Aman.
And okay. Excuse me, before we start, we have another presenter called Sai Shravan Vidichella. Can we include him in the panelist also?
Yeah, Aryan will do. You may get started.
Okay. Good evening, everyone. Today we'll be presenting a paper, Stance Classification with Improved Elementary Classifiers using Lemmatization. Today I, Sarthak Shastri, Aman Priyanshu, Vedant Rishidas, and Sai Shravan will be presenting the paper, and other team members, Harsh Rathod, Shashank Mogia, and Mini Chabra are present in attendees as well. Over the course of the presentation, we'll be going through the introduction, the dataset, pre-processing, proposed models, lemmatization, shuffling of data, presence of class imbalance, implemented models, results, and conclusions. Next slide. Our paper presents a stance classification model designed using classical machine learning methods. In this paper, we use a dataset of tweets which are linked to the hashtag MeToo movement. The phrase #MeToo has been used to empower survivors of sexual assault and abuse over the last decade or so. The movement has spread so rapidly that there have been tweets now present from over 85 countries. The dataset that was provided to us contains 7,978 tweets for training and 1,995 tweets for testing. From this, we were only able to extract 6,799 tweets for training, due to the remaining tweets being no longer available to extract. The tweets were classified into the following categories: text-only informative, image-only informative, directed hate, general hate, allegation, sarcasm, opposition, support, refutation, and justification. On analyzing the data, we found that 7 of the 10 categories had less than 8% positive values, which indicated a large imbalance present in the dataset. Now, Shai Shravan will be continuing.
Thank you, Sarthak. Now we are going to talk about the pre-processing we have done on the dataset. The following steps were implemented in the pre-processing to reduce data noise. The text was converted to lowercase so that there is no distinction between uppercase and lowercase words. Punctuations, text inside brackets, and words containing numbers were removed. Stop words were taken from NLTK to remove terms which provide no information about the content of the tweet. Next slide. Random forest. Random forest is a flexible and easy to learn machine learning algorithm. It is an ensemble tree-based learning algorithm. The random forest classifier is a set of decision trees from randomly selecting subset of training set. It aggregates the votes of different decision trees to decide the final class of the test object. Random forest runs efficiently on large databases and can handle thousands of input variables without variable deletion while giving estimates of important variables. It has an effective method of estimating missing data and maintains accuracy when a large proportion of data is missing. It also has methods for balancing class error in class population unbalanced data sets. Next slide. Naive bias. Naive bias is one of the simplest supervising learning algorithms. Naive Bayes classifier are a collection of classified algorithms based on Bayes theorem. It is not a single algorithm, but a family of algorithms where all of them share a common principle. That is, every pair of feature being classified is independent of each other. It is fast, accurate, and reliable algorithm. The classifier has a high accuracy and speed on large data sets. More tuning can be done with alpha and beta. These are the models we mainly used for a data set. Now I'll like to hand over to Vedant Rishidas.
Thank you, Shravan. So after the required pre-processing, we lemmatize and shuffle the data. The reason we choose lemmatization over stemming is because it does not simply chop off the inflections, but instead relies on lexical knowledge database like WordNet to obtain correct base form of words. And shuffling of data ensure that each data point creates an independent change in the model without being biased by the same points before them. Can you go to the next slide? So here's the representation of table 1, which is the data set at a glance. In this, we can see that text-only informative is the only one which has the highest percentage of positives and is in the majority side of it, while rest of them have percentage of positives in the minority side of it. Can you go to the next slide? So what happened in this is we observed that the data set is skewed towards the negatives in majority of the categories that were required to classify, such as directed hate, generalized hate, allegation, sarcasm, opposition, refutation, and justification, where the percentage is positive is less than 8%. This adversely affected all the models that we trained it through, resulting poor classification due to poor generalization, as we found while testing it on a validation dataset from the training dataset itself. So even AUCs were very high, the AUC ended up to be very poor, and hence we found the presence of class imbalance and decided to handle it using a technique called random undersampling. Can you go to the next slide? So in this, we can see that we have mainly focused on those classes in which the number of data points is lesser compared to the majority class. And for each category, we have decided individual ratio selection for it so that optimal results could be achieved. Can you go to the next slide? After that, after splitting the data and balancing the class imbalance, we tested it through various algorithms and finally settled upon two elementary classifiers, multinomial naive Bayes and random forest classifier. So we used the scikit-learn library's implementation of these algorithms. Under naive Bayes, we classified directed hate, generalized hate, allegation, support, and oppose. While under random forest, we classified text-only informative, sarcasm, justification, and refutation. Can you go to the next slide? So after that, using the test train split ratio of scikit-learn, we decided to maintain a test train split ratio of 20:80, where 20 is represents the test data, since it gave the optimal AUC in almost all the categories except for one, which can be seen in the next slide, that is directed hate. In this, we found that 25:75 split ratio gave the most optimal AUC. And now, my friend Aman Priyansh will be continuing.
Um, can you hear me? So we have talked about various models which we implemented and which we proposed. Finally, coming to our implemented models, that is naive Bayes, random forest, support vector machines, glove embeddings, and BERT. We have worked through multiple shortcomings of each of these models and finally came upon these results. That is, using simply naive Bayes, elementary naive Bayes, we achieved AUCs of 0.5, around 0.5, and so and similar with random forest. However, when we look at modern approaches towards NLP classification, such as glove embeddings and BERT embeddings, we realize that there is a tendency of these models underperforming compared to better proposed models, that is random forest with ratio selection and naive Bayes with ratio selection. We can clearly see this in the ROC curves, which are represented here for generalized hate. As we can see, our proposed model of naive Bayes with ratios proved to give a much higher AUC than our other implemented models, that is BERT, glove, BERT embeddings, glove embeddings, naive Bayes, elementary naive Bayes, random forest, and random forest with ratios, as well as SVM. Looking at only elementary classifiers for generalized height, we can still see, we can clearly see that a lot of them underperform with respect to certain thresholds, thereby reducing their AUC and thereby proving that they are poorer classifiers as compared to naive Bayes with ratios, which is proposed by us. Finally, when we are looking at advanced classifiers or neural networks, sequential neural networks, which are updated with glove and BERT embeddings, we can clearly see that there is a tendency of both of these networks to underfit or to not classify accurately, thereby giving AUC values very close to 0.5. This can clearly be seen when we compare BERT's training ROC curve with BERT's testing ROC curve, where we can see that during training, the AUC of BERT was up till 0.8, whereas during testing it was closer to 0.5. It was clear that these sequential models were vastly overfitting, and therefore we employ different methods to solve this issue. We use BERT with 500 epochs without regularization, BERT with ridge regression plus 500 epochs, with 100 epochs without regularization, as well as reducing the network size as well as employing ridge regression. However, none of them were able to outperform our proposed model of naive Bayes with ratios implemented. Um, looking at the comparison of the two models which we propose, that is naive Bayes and random forest, we can clearly see that in certain cases, both of them complemented each other. Looking at our two chosen classifiers, we can see that in certain cases, naive Bayes was outperforming random forest. Therefore, we chose results from both of them for particular targets in which they excelled at. In a lot of cases, the two classifiers gave us similar results, like text-only information and sarcasm. In other cases, they complemented each other by performing better than the other, thereby increasing our overall performance. Cases where naive Bayes greatly underperformed, such as justification, we can see random forest performing really well, an increase in AUC from 0.46 to 0.64. On the other hand, random forest only gives an AUC of 0.51 for directed hate, which is complemented by naive Bayes' 0.6. Taking a look at our final results, we can clearly see that in a lot of cases, our sequential models, which were aided by BERT and glove embeddings, did not give as good results as with elementary classifiers, which are not only faster but also conserve memory, as well as they are able to clearly distinguish and become great classifiers. Thank you.
Is there any specific reason you decided to lowercase all the text?
Yes, there are specific reasons we decided to lowercase certain texts. The reason was since we are employing elementary classifiers finally, we decided that reducing the vocabulary was aiding it much. Although the results were experimental, and we realized that it was easy. We were getting higher higher AUC results when we lowered the case. However, the reasoning behind that was naive Bayes especially, which depends on word count, especially for NLP classifications, was well performing when it was not able to distinguish between something which was in lowercase and something which was in camel case, thereby giving better results.
Do you feel that if we make a distinction, especially for something like directed hate, if you had something like maybe a sentence in all caps versus a sentence that's all small, do you feel that uh, what the sentence that would be in all caps but potentially has some more context to it, or do you feel that the amount of information lost in lower casing a sentence versus having its case information is insignificant.
Or perhaps having a few named entities, right? So directed hit by itself implies that you have an entity or a person with whom the hate is directed to. So perhaps you could have identified noun phrases or pronoun phrases and like use that as an aid to classify. Like, what do you think about it?
Yes, there is an issue because of loss of information by lowercasing multiple sentences or different tweets. However, we are including that in future works, and for the implementation with respect to BERT as well as glove embeddings, we were able to give them the complete like retaining the cases, we were able to give them that information. However, when it came to knife bias and SVM, the results were not as great because of more there was more bias with respect to introducing case sensitive information.
Okay. Also, you use two different models. Like, if you could go one slide before, I think the one where you were discussing the random forest and yeah, that this one. So, did you think about trying to ensemble these models or like do a combination of both of these classifiers, seeing that as you in your words you said that they complement each other in cases where one works better and the other doesn't, and that's what your observations also show. So do you think, or have you given a thought to an ensemble of these two classifiers or a bunch of different classifiers which might, where one weak classifier might excel on some tasks and a different
We
classifier
were
might excel in the places where that's weak?
Yes, we started working on an ensemble algorithm which included naive Bayes random forest as well as SVM. When we finally decided on selecting elementary classifiers as our main implementation. However, the reasons why we finally did not take random forest, naive Bayes or SVM together as an ensemble classifier was because we were going we first of all one of the main issues that were occurring is if we had voted results, one of the classifiers, especially since they complemented each other, there were effects due to which SVM or random forest would reduce the AUC which we were getting by naive Bayes alone, and in certain cases it was vice versa. That is, random forest's AUC was like uh, if we individually implemented random forest, its AUC would reduce because of the other two classifiers.
So that would only happen in the case if the classifiers that are reducing the performance, they are actually doing bad on the examples that the other classifier is doing well on. Have you done such analysis to support this statement, or is it more like you think that this would be the case?
We experimented and we have results for those, but at the same time, they were not as well. They were not performing as well as even baseline worst situations because of our results with SVM, which were further decreasing what we had achieved with naive Bayes and random forest alone.
Okay, given that you're giving the same features, let's talk about, we'll make this quick, but let's talk about generalized hit, 0.58 and 0.52. Is it that the random forest is doing bad on a bunch of examples that the naive Bayes is doing very good on, or is it that there's a certain category that both of them can't do well on? Have you looked into this or have you not?
We have looked into the cases where random forest was working lower or poorer compared to naive Bayes, and there were reasons because random forest, being a tree-based classifier, was able to distinguish certain tweets, collect words. In certain cases, where some of the negative tweets and positive tweets were very had similar words, and because of that reason, random forest was not able to give that same similar results. On the other hand, since it handled the random forest, it retained the due to bootstrapping, it retained the basic sequences of the sentences. However, on the other hand, naive Bayes, having the bag of words method, simply had the probability values of different words being present in the positive, as positive cases and as negative cases, due to which it in certain cases it was outperforming random forest.
Okay, makes sense. Thanks.
Okay, good. So we can move to the next presenter. So the next presenter, whom do we have from the list?
Yeah, I'm Devapriyo.
Okay, Devpriyo. Yeah, so please go ahead.
Okay, I'm waiting for the presenter access. Yes. Just a moment. There is a problem why I am not able to share my screen. Uh, okay, actually, I think I need to quit the meeting and join. Apparently, I need to restart uh, for for giving myself the access to present or something. Can you just give me 1 minute? I will just join back.
No issues. Should we go ahead for the next presenter and we can?
You can do that. I think I just have to restart Cisco WebEx once. That's the problem.
Okay, we can wait.
Okay, just 1 minute. Okay, I'm back. Yeah, thank you. Now I can actually share. Yes, can you see the screen?
Yes.
Yeah.
Okay, thank you so much for the. Okay, so the title of the presentation is Transfer Learning with Augmented Vocabulary for Twist Classification. Actually, the work was all done by the two students, Vineet and Karthikeya. Unfortunately, they had placement screening test just at this time, and they prepared all the presentation and everything, but I'm having to present it. So hopefully I can, do honors properly. So the topic was oops. Yeah, the topic was our challenge was Me Too Grand Challenge, which is essentially classifying a set of tweets, and there were into a set of linguistics aspects which were relevance, hate speech, sarcasm, dialogue acts, and stance. And both text and image were available for most of the tweets. We did this in a project mode, so basically mostly numerical work and less of a research, basically trying out what works better. Some of the images had textual banners. They could be converted to text, which we could not do. So what we ended up doing was we essentially worked only with the textual part. So it's an NLP only work. And we tried several machine learning models, out of which tree-based and deep learning models worked the best for the task. Yeah, it was nice that our best performing approach was ranked first on the leaderboard when the challenge finished. So it's a Kaggle hosted competition with the evaluation metric was area under the ROC curve. The dataset had only tweet IDs because of Twitter legal requirements, and which meant that the participants had to download the tweets directly. Although there are about 8,000 tweets in the training set and around 2,000 for the test, when we actually hydrated the tweets, we were only able to hydrate around 7,000 for the training set, because we started a bit late, and by the time we actually downloaded the tweets, many of them are already deleted. There were 10 data labels of this out of these 5 categories, and as other speakers have already mentioned, the data suffers from severe class imbalance. But there are some interesting points to note here. So obviously there is this text-only informative and image-only informative where the class imbalance is not that severe. But look at the next 5. So the 2 hate categories, very few positive samples, and sarcasm, very few, and the dialogue acts also, right? So very few positive samples. Again, for stance, of course, there was quite a lot of imbalance, but not that stark. So which actually meant, because the evaluation metric was AUC, well, playing safe on these 5 categories in the middle actually would pay off well, right? So actually that's one observation. So although we tried many different classifiers and they actually worked differently well for these methods, our title is based on what worked well for the last 2 cases, the support and oppose, because there I think our insights were interesting. I'll skip the processing part because we actually didn't do much. We did not do removal of stop word or stemming, because usually for sentiment analysis, those things are important. This is kind of a sentiment analysis. So TF-IDF vectorizer was used to represent the tweets into TF-IDF form and so on. So this is not the most this is not the highlight of the talk. So I'll just skip this. Let's talk about that. So initially, we tried just test running the most basic classifiers. And then we went on to try the tree-based classifiers. They're all libraries available, so one could try them easily. And finally, we went on to try the deep learning frameworks. So first by LSTM, which others have also tried, with GLAB embedding as usual. And transfer learning architectures, well, we had high hopes on these, of course. So BART, transformer based, and then fine tuning and ULM fit. ULM fit is actually the main point that we are going to see later in the talk. So obviously we did not try one classifier for all kind of an approach. Like many others, for each of the classes, we chose the final model based on the AUC score obtained on the training and validation set, just to prevent overfitting, because that some part of the test set obviously were not given to us, which is the reasonable thing to do. So logistic regression, multinomial naive Bayes and SVM. So we did the initial runs. Actually, they did not work so well, but SVM did not work that bad in some of the for some of the classes. But then for the severely imbalance, for the classes for which we have severe class imbalance, the tree-based methods saved our life to some extent. So overall, XGBoost, which is actually a very relatively modern technique, it's actually ensemble based, right? So it actually tries to construct several kinds of trees and then takes the best kind of a thing. So which is the way to go for most practical applications. So XGBoost actually produced reasonable scores for these 5 labels: image on informative, and then the sarcasm, justification, refutation, and allegation. the tree-based models worked, performed really well, mostly XGBoost and then for allegation random forest. So BiLSTM is one obvious thing to try because it generally works better with sequential classification tasks. So what we did was we took pre-trained graph Twitter embeddings and implemented BiLSTM using bidirectional layer wrappers in Keras. And we used dropout also and the conv1D filter for the context capturing. This worked better than other methods for the hate speech part. Okay, so only for the hate speech part, this worked better than other methods. Actually, SVM also worked reasonably well for generalized hate, but we ultimately stuck to BiLSTM for our submission. Okay, yeah, so then we went on to try BART, and BART is supposed to be the state of the art in NLP, especially when we want to do transfer learning, and transfer learning was definitely the way to go here. So here the main problem was that yeah, so let's actually talk about what we did. So we fine-tuned BART with Adam optimizer, and these were the exact learning rates at the end that we used. So yeah, that's the BART architecture. And we achieved decent accuracy, but accuracy is not the AUC because there are a small number of positive samples. So BART did not produce very good results for directed hit or generalized hit or even the stance classification. Even BART with random oversampling, so we tried to see whether some oversampling would improve the results, actually had no positive effect. So one of the problems was that most of the vocabulary in the #MeToo hashtag, I mean tweets with the #MeToo hashtag, were unrecognized by the BARTs. We actually used a smaller BART. The students did most of the things on Colab. Yeah, they were not recognized. So which then led us to try ULM fit. So the fundamental idea behind this is to tackle the problem of insufficient data or the vocabulary mismatch. So the idea here is the following, that you have a general domain language model pre-trained, and you have a target domain language model. You fine-tune the general domain language model, okay? And then you again fine-tune for the target task language model, and then finally you have a classifier, right? So, so ULM fit language model was pre-trained on Wikitext 103 corpus. What we did, we added a lot more tweets. Okay, we added a lot more tweets. We augmented a lot of vocabulary, total around 200,000 tweets, including our original data. So our original data is about 7,000 tweets, right? So we actually added a lot to augment the vocabulary, and then fine-tuned using the fast. So we use the fastAI.text tokenization technique, and then fed the dataset into the language model, which is essentially LSTM with no attention. So it's a bit surprising, and we'll see the results. It's a bit surprising that this actually worked pretty well for the stance. So yeah, so to avoid catastrophic forgetting, so to avoid destroying that everything was pre-trained, we used the gradual unfreezing bit carefully, so that the learning rate was chosen in the following way. It's just a technical details. And here we have the results. So yeah, so what we found was that SVM worked kind of okay, but well, only for one class generalized hate, it was kind of okay. The tree-based models worked well for the classes which have huge imbalance, and the deep learning models, especially the ULM fit with augmented vocabulary, worked significantly better for the support and oppose. Now, because the support and oppose actually had a good number of positive samples, the AUC scores were boosted quite a lot for this particular, I mean, this for doing well on these two classes. So that's actually very important. All right, so just summarizing quickly. So the main challenges faced here were the dataset was small, which was good because we could run the experiments quickly, but actually, contrary to our intuition, the deep learning models did not work that well, especially BART. So several class imbalance was definitely another challenge. These are all real challenges. Social media expressions are anyway not easy to classify, especially Me Too kind of things, right? So people are extremely sarcastic all the way. Lessons or findings for imbalanced classes, tree-based methods. BiLSTM performed well for hate speech, and transfer learning with ULM fit plus augmented vocabulary worked well for stance detection. But did not perform as well as we expected. Scope of more work. Well, this was definitely an NLP only approach. We did not use the image data at all, which means we can. And then more pre-processing could be done, especially for emojis or post tagging and many other things could actually improve the input embedding into any of the models. Yeah, so we didn't have time to do those. Obvious approach to include the images would be actually many of the images are just textual banners. So people are just putting up a textual banner, which is actually an image. So one could run OCR on those and then take them as text. The trouble with using the other images are that those are very abstract. Even for human beings, looking at a tweet, it will be hard to figure out what is it trying to say. But in general, definitely, like many others have tried, so some combined architecture of the images and text would definitely be on the cards. Well, so that's basically what we did, and thank you. So I would be up for questions.
Okay, thank you so much. So questions?
Yeah, first, thank you. Like, I think this was a pretty great presentation. Some of the insights are things that we've also seen when we were constructing the data set. And in fact, the model that we presented initially on this work was also a ULM fit model, very, very similar to what you've done, in fact. So I think most of your findings are pretty helpful and in sync with what we've done. A side note before I ask a question I followed your work previously, and I think like your Sigayar work on query suggestions is really great. That being said, I just have one question. I see that you added a lot of data in terms of further increasing the vocabulary for ULM fit, which is something we've also done. I also see you've specifically chosen tweets and the semi-val data set, etc. Do you feel that perhaps because our data set is fairly small, and in fact, I'm not sure if it's something that we've mentioned in the challenge, but like given the specific time that it was taken from, along with the fact that there is some demographic information available as well, do you feel that perhaps having additional data, like specifically fine-tuned from those specific demographics, particularly like in our case, we have a larger sample bias from India and the US, for example. Do you think that selectively adding more vocabulary would help, or do you, just based on your intuition, or do you feel that
Yes,
a more generic
absolutely.
corpus is something that's helpful?
No. I mean, obviously, intuitively, this is a very domain-specific task, and that is one of the reasons I think BART, the pre-trained general BART, did not really work well. So yes, definitely augmenting more vocabulary with specific targeted tweets would definitely help. Yes, I mean, one could actually do a lot on this topic. There are a lot of scopes to do things.
Right,
Also,
and
just
then sorry,
yeah,
go on.
no, you can go ahead.
Okay, I just wanted to check then, you only used the regular pre-trained BERT. Like you've not fine-tuned it, or
Oh no.
there are like newer variants of BERT, like BERT tweet, for example, which are trained on like millions of tweets. This is like just the standard BERT, and you've
No,
not compared with any fine-tuned versions.
right. No. So it's actually I mean, we fine-tuned it, but it is the regular BERT. Yes, regular BERT fine-tuned. Right.
Okay, got
So
it.
regular but
Makes sense.
fine-tuned. But yes, I mean, now there is also ExcelNet and many other things, right? So, but yeah, I mean, it's, as we said, it's basically a project mode kind of a thing. So students,
Right.
wanted to do a project. So it was more like numerical testing, trying out many algorithms kind of a thing. So less research in that sense. Yes, definitely.
Right. Makes sense. Makes sense.
Yeah, so also just a side question. So while augmenting vocabulary, I see that you have used tweets from semi-val, right? I guess due
Yes.
to, since there's a matching domain as well. So correct me if I'm wrong. I assume that you are doing this just for the support and post classes, right?
Right, right. We did this and tried it. So if you look at the results table,
Mm-hmm.
so we tried it on the directed and generalized hit also,
Mm-hmm.
but the performances were more or less at par. Now, one can argue whether 0.52 and 0.50 is there actually a lot of difference, and 0.51, right? I mean, we
Mm-hmm.
are only testing it on so few positive samples.
Yeah.
0.52 and 0.51, 0.50, well, they're all kind of the same. 0.58 or 0.73 compared to 0.51,
Yeah,
yes,
that's a major improvement.
that's a
Yeah.
major improvement, and that actually
Yeah.
worked well. But
Yeah.
look, the others actually, I mean, there isn't really much to talk about there. So it's basically just like a game. You try
Yeah.
and see what works better. You improve by this point number, and also
Yeah,
yes.
so my question basically was pointing to the side that how easy or difficult was it for you to find tweets for augmenting your basically ULM fit model for other classes, like not just support and oppose, but for other ones such as allegation justification, because I know this is specifically this is highly domain specific, but yeah, I mean, what was your observation regarding this?
Okay, so no, so to be honest, actually, this once XGBoost worked really well for these classes with very few positive examples. We did not actually try augmenting augmenting vocabulary method on those classes there. We actually focused more on just the other 4 classes. It should be attributed to kind of lack of time and so on, but then again,
Yeah,
I mean, the number of positive samples are very small anyway.
sure, seems perfectly reasonable.
Yeah.
Okay, so thank you so much. Indeed, a very nice presentation. And
Okay, so I'll
yes, we
stop
will.
sharing and yeah,
Yeah.
please move. Yeah.
So we will go for the last presentation of the day. So who will be presenting? Azan?
Yes, so I'll be presenting
Sure.
along with my teammate Sajjad Jafri.
Okay.
If you could just unmute him for a minute. Like he cannot join the panelist due to some issue. He's
No
in the
issue.
attendees list.
Yeah, so Aryan, please help him to unmute.
Just have unmuted Mohammed Jafri. Yes, please.
Okay, am I audible?
Yeah.
Azan, can you start present?
Yeah, sure. I'll just start presenting my screen if I would be allowed.
I'm allowed. Can you please check?
Yeah, sure. Thank you. Is my screen visible now?
Yes.
Okay, let's. Yeah.
Okay. Good evening. I am Mohammed Sajjad Jafri, and I am with my teammates Mohammed Azan and Mohammed Ahmed. We participated in the IEEE Big MM 2020 Grand Challenge, which was based on using sentiment analysis for understanding tweets that were related to Me Too. Next slide. Next. Okay. So the task that was given to us, we were given a data set of tweets. The objective was to classify that it was a multi-label binary classification. We were given multiple, like 10, I think we were given 10 classes, and we were supposed to classify the given tweets into those 10 classes. And the binary labels that we had were either 0 and 1. So the tweets that were collected were related to the Me Too movement. The movement was started by activist Tarana Burke in 2006 in support of victims of sexual abuse. So recently, the movement has gained a lot of momentum, and people have been reacting to it in different ways. And so our task was basically to analyze how the movement is, how society is being impacted by the movement and how society is vice versa impacting the movement. Next slide. Okay, so the data set consisted of 10 classes. As the previous presenters have already claimed that the data set was the data set was highly skewed. So we have, in cases like directed hate, general hate, sarcasm, allegation, justification, and refutation, we had significantly low number of positive samples, and the for initial two classes, that is text only informative and image only informative. So text only means that the tweet only had textual data, and image only means only had image data. So we had more number of tweets that were providing textual data. So this was pure NLP based approach that we started with. So Azan would be continuing with the pre-processing methods. You can mute me now, sir.
Yeah, so good evening, everyone. I'm Mohammed Hassan, and I'll be continuing from here. So the very first step of our task was to pre-process the data that we have been given. Now, since the tweets cannot be shared with the text, so we were given the tweet IDs, which we had to extract the tweet data from using the Twitter developer API. So from the that was curated by us, not all the features were necessary, like the features like username and the tweet times were acting as noise. So we did not need to use all the data set that was given to us, and we selected only the selected columns that we had to use. And it was seen that pre-processing helped us to increase the AUC with a increment of 0.03. Now this was a very small increment, but since this was majorly, we annotated this to the class imbalance. Now the very first step was to tokenize, and to tokenize the tweets we used the NLTK library for Python. The next step was we used the hashtags and segmented them and removed the hash symbol and added those hashtags to the tweet text. Then we converted the emojis to the text counterpart using the emote library for Python. For example, a laughing face emoji was converted into face laughing, and similarly a girl emoji was converted into the text counterpart of a girl. Then we proceeded to remove the special characters and stop words. For example, the symbols like hash, @, percent, dollar, brackets, etc. were removed. And we also replaced the URLs and numbers with the bracket of URL and numbers. It was seen that URLs actually don't give much importance and act as noise. So it was better to remove any URL with brackets and URL. And at the end, we corrected the wrong spellings and typos, which showed that the performance increased. For example, the sentence "I have good spelling" was corrected to "I have good spelling." It was seen that correcting the spellings had impacted the results deeply, because words like HAVV, GOOD would not be recognized as words and would not. I'm sorry. It was seen that words like HAVV and GOOD could not be recognized by the vocab library. So then we proceeded with the data extraction. From the iterated tweets, we only used the columns, hashtags, and text. We converted both of these into a single column where the text was pre-processed and the hashtags were pre-processed and then added together. For the models, we have used, for the text, we have used to convert them to the embeddings using the glove embeddings, which was used. The glove library we used consisted of Twitter 6 billion dataset and BERT embeddings for a model. The sentences were given a maximum length of 256 and short sentences were padded so that each sentence has an equal length. The deep learning models that we used were convolution neural nets and bidirectional LSTMs and a BERT model. The CNN that we used was totally based on a similar model used by Mr. Yaman Kumar from IIIT Delhi, which he used for a semi-viral task in the year 2018. So our CNN model had 3 layers and the kernel sizes were 5, 7, and 8. Each kernel had 52 512 filters each, and the final layer was a dense layer having 10 units with sigmoid activation. So what we first did was we used the sentences, passed them through the convolution layers, and then max pooled them together. And this was then given to the output dense layer, which had sigmoid activation. The reason why we used sigmoid activation instead of a softmax layer was basically each was majorly because it was a multi-class classification model. That means a sentence can belong to more than one classes. So using a softmax layer would have not been that useful as compared to a sigmoid layer. The bidirectional LSTM that we used consisted of two layers. Both of them were bidirectional LSTMs. The reason we used a bidirectional LSTM layer rather than a single layer, rather than a unidirectional layer, was basically to annotate the position of each word in the sentence. For example, since each sentence is a sequential data, the position of the word impacts the meaning in the sentence. Therefore, we have used a bidirectional LSTM layer. The LSTM layers had 128 units, and the final layer was same, dense, having 10 units and sigmoid activation. The next model was a pre-trained BERT, where we used a BERT large uncased pre-trained model. We did not fine-tune it due to the time constraints, and the final model that we used was an ensemble of the above three models. We had seen that each model performed very well on some classes and performed poorly on other classes. So what we tried to do was incorporate all the three performances into a single model that was obtained using an ensemble. The ensemble took the probabilities from each of the models and averaged them. Now, each of the models were trained that were given to the ensemble were trained using the same number of reports, were given the same learning rate and the same loss function. And here are the results that we obtained. The private set score was seen to be high for ensemble, whereas the public set score was low. As for the BERT obtained a very low private set score, whereas performed high on the public score. For the further work, we had decided to balance the classes. As Sajjad mentioned earlier, the classes were highly imbalanced, and we tried to work on balancing the data set, which we could not. So obviously, we are further looking to find a way where we could balance these imbalances. And thus, another feature that we would try to work on was extract data from the user comments. It was seen in some papers that extracting the user comments and passing them on to the model can help us to annotate the exact label. And since we only worked on the text that was provided and did not work on the image, we would like to work upon the attached images as well. That brings me to the end of our presentation. So any questions?
Yeah, thanks Azan, thanks Ahmad. So any questions for them? Akash, Ramit?
So no questions from my side.
None from mine either. It was mostly clear.
Okay, very good then. Thank you so much everyone, and thanks for staying so late, and despite we started a bit late, so thanks for your patience. And many thanks to all of you for supporting the Grand Challenge as well as the conference. I would also like to thank Ramit, Akash for organizing this Grand Challenge, Shivangi as well for organizing this Grand Challenge, which required much effort from their side as well, uh, from the task creation, then evaluation and reviewing and so on. So thank you so much all of you, and it was indeed great pleasure working with you. And this would have not possible without your support, making the conference a successful event. I must say, I mean, it was a great event. and this is the last event of the 3 days conference. And I'm very happy that it went so well, and we had so many very good events, keynote, grand challenge, workshop, regular papers. I would also like to thank all the volunteers, especially IEEE student branch uh, students, because they have really helped throughout all 3 days to run the conference smoothly in the virtual event, because it would have not been possible without their support running the conference very smooth. Thank you so much, everyone, and have a great day. And regarding the best grand challenge paper, we will be announcing probably in a few hours on our social media pages, along with the best undergraduate student consortium paper. So thank you so much, and we will also let you know through the emails. Thank you so much.